Hey kids, let's do some more fundamental theorem with line integrals, except we're gonna do it in 3 dimensions. Woot woot.
3 dimensions.
Thanks, Mr. Getz. All right. So here we go. Find the potential.
Potential.
Oh my goodness. Oh my, I can't concentrate anymore. So, all right, so notice the difference here. Then the problem we did before was obviously we have 3 components, and remember, think cap F goes with the antiderivative, right? So, or derivatives. Look, he's got me all messed up. You are looking at derivatives, right? Each one of these is a derivative, a partial derivative. So if I want to get the potential F, I want to prove that I want to show that each one of these is a bunch of partial derivatives. So how do I get the original? I don't have to show that it's conservative. Remember, I gave you a theorem for doing this in 2 dimensions. You had your partial p, partial y, had to equal partial q, partial x, right? This is later. There is a cool theorem for this, but before, I want to just get to the algorithm of what we're doing for finding potentials with 3 variables and 3 dimensions, and we'll get to this theorem about verifying that I'm conservative first. So for your homework problems that are associated with this, all your homework problems, you don't have to even think about they're conservative. They all are conservative. Okay. So if I'm looking at derivatives, y squared is a derivative, partial, right? Partial f, partial x. This is partial f, partial y. This is partial f, partial z. I just copy, paste, copy, paste, copy, paste. And I'm going to try to get f by itself here first. I'm going to tackle x first, and I'm going to partially integrate with respect to x. So think about what that would look like. Right, taking the y squared is a constant, so its derivative would be the constant times x to the first power up divided by the power up plus a constant, right? And again, just take the derivative of this. Take the derivative, partial derivative with respect to x, you would get y squared plus nothing, right? So it's just that this plus c though, remember when we were just doing with 2 variables that I told you to think about this because you're doing partials? This could have been a function in terms of y. Well, guess what it could have been now? It could have been a function in terms of y and z, and it would have disappeared, right? Think about it again. If you took the partial of this with respect to x, you would get y squared, and if this was some function in only y's and z's, you would say it was 0. It would go away. So when we try to get it back, we have to recognize that that might be there. So now we're going to solve, just like we did before, though, we're going to try to solve for this c by differentiating with respect to y. So I'm going to get a g prime. So notice, though, I am differentiating with respect to y here. So 2y, right? Bring down the 2y and the x, plus the derivative here, g prime, with respect to y. But notice this magic. And again, this is the same as it happened before, right? Here is the partial f, partial y. Partial f, partial y, just substituting. If partial f, partial y is equal to 2xy plus g prime of yz, then what partial f, partial y is equal to must be equal to 2xy plus g prime of yz. And notice what happens. Bye-bye. Bye-bye. Which means just e to the z. Let me erase that. Just e to the z is equal to g prime. And remember what I'm after. What am I after? I'm after g. What can I do now? That's right. Partial integration, this time with respect to y, though. See what's happening? Partial integration with respect to x. Differentiate with respect to y. Partial integration with respect to y. E to the 3z was just a constant, right? So when you anti-differentiate, you get y to the first over y over 1 times the constant, plus now, though, I am just dealing with my constant being another function in terms of z, right? That's going to equal g of z, not g prime, but g. Now what? Well, remember our big goal. Our big goal is to try to get f by itself, right? We are trying to undo the gradient, right? The gradient is full of partials. We're trying to undo it. So we got part of the way, pun intended, here. We got one of them. Now we wanted, there's two more potentially. I got g of yz. I can now replace this, right? Right? Copy, paste. So bye-bye to that. And now I can write little f is y squared x plus g of yz. But I found what g of yz was equal to. Now what? I'm 2/3 of the way there. What do I do now? Now I'm going to solve for this new c by differentiating. Notice over here, I differentiated with respect to y. What am I going to do? Differentiate with respect to z. So differentiating this expression, right, or this equation with respect to z, this term goes to 0. And then I get y e to the 3z times 3. That's what I have there, plus h prime of z. But if df dz is equal to this, and df dz is also equal to 3y e to the 3z, what happens? Straight up substitution, and bye. And I end up with 0 equals h prime. Was h prime what I was after? I don't think so. I was after h. How do I go from h prime to h? Oh, snap. Anti-differentiate 0, and I just get, actually, ta-da, finally, c. So I don't need that equation anymore. Little f 1/3 of the way done. Little f 2/3 of the way done. Little f done and done. Now, how can you check your work? Right? Take the partial of this expression with respect to x. Guess what you're going to get? Take the partial of this expression with respect to y. Guess what you're going to get? Yep. Take the partial of this equation with respect to z. Guess what you're going to get? Yep. Take the partial with respect to I don't care, with respect to a constant, you're going to get 0. Right? Woohoo! Now remember what the whole reason we were doing this, though. Why do we want to do this? Why do we care about going through this whole process? Because remember, you're going to be asked to find a line integral. So this whole process is so that if you are asked to take capital F and do a line integral, You are going to replace capital F with the gradient of f, because you're conservative. Remember, I'm telling you this is conservative. And since now capital F is actually full of derivatives and you're taking an antiderivative, remember, by, and you just have, derivative and antiderivative stuff goes away, and you're just doing f of stop minus f of start. Fundamental theorem. Craziness. So let's do one. So for that example, all they were asking us to do was to find the potential, right? We're done. Find the potential, over. Now here for this one, this is part A, is find the potential. So let's go through this, and then part B will actually use these to integrate. So if you want to pause the video and see if you can do this on your own, fine. Or you can do it with me. So remember, you're looking at derivatives. Each one of these is a derivative. So we have 3 partial derivatives. So our job is to try to get little f, right? If it is true, remember, we're assuming conservative. So the gradient of f is equal to f, meaning these are all derivatives. So the first thing I want to do is anti-differentiate the first part. My pen is a little frozen here. I don't know why. Come on, pen. So while my pen is having trouble here, you anti-differentiate that first part. I can use it with my trackpad. No, I can't. I'll wait. Oh, I think it's back. Sorry. All right. So, because it's conservative, which you don't have to worry about proving now or showing, gradient of f is equal. So here's copy, paste, copy, paste. This is partial f, partial x is 2x plus y squared z. Partial f, partial y. Jeez. So start here. And let's anti-differentiate with respect to x. So when you anti-differentiate with respect to x, you're going to get x squared plus what? X to the first over 1 plus your constant. What's your constant look like in terms of the other 2? Now remember, you want to get here. So that was step 1. Step 2 is differentiate with respect to who, though? Differentiate with respect to y, and x squared goes away, and you get 2xyz, right? Plus the derivative of this thing. Now what? This is partial f, partial y. This is partial f, partial y. Substitute. 2xyz is equal to 2xyz plus g prime by 0 is equal to g prime. But I don't want g prime, I want g. What do? Anti-differentiate with respect to who, though? dy. Should have put a dx up here, shouldn't I have? Anti-differentiate a constant, you get a constant. But be careful, you still have that extra variable, right? And the antiderivative of a derivative goes away. And I have yz. So now take this right? Bring this blue F down here. That's not a prime. Remember, that's next to the first. I was just being a little overzealous there. Now it's like lather, rinse, and repeat, right? I am going to, well, let me do it down there so I don't have to rewrite this. I am going to differentiate with respect to who? Z. And what am I going to get? X squared is going to go away. This is z to the first, so just xy squared plus h prime. That is df dz, partial f partial z, but here's partial f partial z. So what happens? Bye. And I get 0 is equal to h prime, but was h prime what I was after? Nope. I was after h, so anti-differentiate both sides with respect to z. That's a z. I know I wrote an x, but you know it's a z. And when you do that, you get c is equal to h of x. Now you're going to take this f over here. Ta-da! What is f? F is what is x squared plus xy squared z plus c. Ta-da! How can you check your work? Take partial f partial x. Check. Take partial f partial y. Check. Take partial f partial z. Check. Now, that was only part A. What do you think part B is going to be? Use that potential function to evaluate the line integral. Oh, gosh. But what is that equal to? That is actually equal to the line integral of the gradient of f, but that is the derivative, the antiderivative of a derivative, by, and that is just f at stop minus f at start. Well, what's my stop and start? So our f from the previous slide was x squared plus xy squared z plus c, but again, because c is just a constant and I'm actually going to evaluate, right, I'd have a plus c with each one of these, but then I would subtract it, so I don't need to write it down. So 2 squared plus 2 times 3 squared times 0 is just going to be 0, right? Minus 1 squared plus 1 times 0 squared plus I don't care is also 0. 4 minus 1, aka 3. All that freaking work for a 3. Are you joking me? Wow. But notice I did all that work, so I didn't actually have to anti-differentiate this. Get it in terms of R of t and right, all that kind of nonsense. Let's do another one, part C. Okay, use the same potential function to evaluate this line integral, but I've given you R of t this time. Uh-oh. F, though, is in terms of x's and y's and z's. Head scratch, head scratch, head scratch. Oh, wait a second. This is x. Right? So what is R of stop? Isn't R of stop sine of pi over 2 plus pi over 2, 2 times, I'm sorry, pi over 2, and 2 times pi over 2, right? And what is R of start? Oh yeah, I love this. 0, 0, 0. So what is f of stop then? This is just going to be a bunch of zeros, right? And what's going to go over here? 1 squared, aka 1, plus 1 times pi over 2 squared times pi plus nothing, honey. And what do I end up with there? Ta-da! There you go. All right. So fundamental theorem day 2 really was nothing new. Same kind of algorithm, just with your extra step. All right. Have fun with that homework, and I'll see you in our live session.